chapter solutions part 6. In the previous class, I explained you about Henry's law applications and numericals related to Henry's law. Now, in today's class, we are going to discuss about vapor pressure. What is meant by vapor pressure, factors affecting vapor pressure, and how this vapor pressure is related to solutions chapter. And next one is Raoult's law. Raoult's law is of two types. Is here Raoult's law for volatile and Raoult's law for non-volatile solute. Two cases is there in our syllabus. So in this class, I am going to discuss about vapor pressure and Raoult's law. First, before starting, we will see some examples. You check here in this figure, here one liquid is there in this glass. This glass is kept in dark, not in sunlight. In a closed room, in one room, you kept in dark. After 2-3 days, this level becomes less. This level decreased, liquid level decreased. After next another 2 days, further decrease is there in the level, liquid level. After another 2 days, so further decrease is there. That means from this to this, from this to this, so there is a decrease in the level of this liquid, even though it is kept in dark medium in a closed atmosphere. Why? Now, what may be the reason for this decrease in level of liquid? So, one more example we will see. So, nowadays in rainy season, you can see the water on roads like this type. During rain, after some time, after 1 hour, 2 hours, so it becomes normal. After 1 hour, 2 hours, it becomes normal. Why it becomes normal? Anybody putting fire nearby this water or under this road? Anybody putting fire? No. Then what may be the reason? You will see one more example. You take one glass water, keep it in sunlight. After 2-3 hours, you can see the water level is decreased. In sunlight, water level is decreased. In the previous case, water level is decreased even in closed and dark medium also. So why this water level is decreased? So this concept is related to evaporation. What is that? Evaporation. So now we will see what is evaporation. What is meant by evaporation? Evaporation or vaporization. Evaporation or vaporization. So in an open vessel or lakes, or ponds, level of water decreases in summer due to phenomena of vaporization or evaporation. Not only in summer, it will take place even in rainy season or winter season also. Okay? Why? Now that is it evaporation will take place only in summer? No. Every time, everywhere it will be there. So you see, you check this slide. In this game, it is one type of game, you know this one. In this game, why this person gone down? Because he lost the game. Loser. He won the game. So loser gone down. Those who lost the game, this loser gone down. So you can see next So this one, winner raises and is raised and upside and the loser downside. Same like in this type of game, you can apply this game to our chemistry also. Here also one fight is there between these two molecules. Between these two molecules fight is there. So these two molecules collide each other. This is one molecule, this is another molecule. Collisions will take place. During collisions, if this molecule gains energy, it will go upside. If this molecule lost the energy, it will go down. During collision, energy change will take place. If molecule gains energy, it will rise up. If molecule lost the energy, it will go down. Okay. So next, same thing is applicable to our present topic. That means you can see in this, all these are molecules, liquid molecules. This liquid molecules because of collisions, between molecules will take place. Suppose you see these two molecules collide each other. If this molecule gains energy, it is converted into gas. So liquid molecules during collisions, they will gain, some molecules will gain energy and will convert it into gaseous state. That means those who gain energy, that one converted into gaseous state or vapor state. Now you see here, this liquid water level is decreased. Why water is level decreased? Inside this water, liquid molecules undergoes collisions. During collisions, some molecules gains energy. That molecules converted into vapor. So in an open vessel or lakes or ponds, level of water decreases in summer due to phenomena of vaporization or evaporation. What is meant by evaporation? So evaporation, the transformation of liquid to vapor form. The transformation of liquid to vapor form is vaporization or evaporation. Evaporation of liquid is an endothermic process. You have to remember this one. According to Lecture-6 principle, high temperatures favors endothermic process. That means vaporization or evaporation increases with increase in temperature. Next, it is explained on the basis of kinetic molecular theory. That means why this evaporation is taking place? Because of collisions. Why collisions? What is the reason for collisions? Molecules moves randomly. Liquid molecules moves randomly in all directions. The molecules of liquid are held together by the intermolecular forces of attraction. The kinetic energy of liquid molecules is different, but their average kinetic energy is. Molecules at the surface will have more kinetic energy than molecules at the bulk. Molecules at the surface will have more kinetic energy than molecules at the bulk. You can see here these surface molecules. Here surface molecules have more energy than the molecules present at the bulk, because in between collisions may take place. Because of collisions, if the molecules gain energy, those molecules will rise up. The molecules who lost the energy, they will come down. That means the molecules present on surface, they have more kinetic energy. So this point is important. The molecules with higher kinetic energy overcome the intermolecular force of attraction and escapes into atmosphere. That means the molecules present at the surface, that molecules only have more chances to go to vapor state. The molecules with lower kinetic energy remain in the bulk. So kinetic energy when compared to earlier state is less, therefore temperature decreases during vaporization. Vaporization or evaporation causes cooling. Evaporation causes cooling. So that means liquid is converted into gas, then some molecules is gone evaporated. That means what about the temperature of this liquid? This liquid molecules kinetic energy decreases, so temperature becomes less. So evaporation causes cooling. The number of molecules escaping from the surface of liquid per unit time is known as rate of evaporation. Rate of evaporation depends on 4 factors. One is nature of liquid, surface area, temperature and flow of air. So nature of liquids, some type of liquids they undergo evaporation more easily. Some containers, depending on container surface area also. You can see here in this example, you take one test tube which contains some liquid. So this test tube has a small surface area, whereas in this beaker it also contains some liquid. Here this beaker this container has more surface area, large surface area. Because of large surface area, more molecules get evaporated. Because of small surface area, less molecules get evaporated. So it is about evaporation. Next one is condensation. Next one is condensation. Now what is meant by condensation? What is meant by condensation? Conversion of liquid into gas is called evaporation. So conversion of gas into liquid is called condensation. The conversion of gas molecules into liquid molecules is called condensation. At one state there exists an equilibrium. There exists an equilibrium between liquid molecules and vapor molecules. This is called equilibrium. Equilibrium. There exists equilibrium. That means rate of evaporation is equal to rate of condensation. The state at which rate of evaporation is equal to rate of condensation is called equilibrium state. Equilibrium state. This state is important for us next topic. So what is next topic? Vapor pressure. In vapor pressure, this equilibrium is needed. What equilibrium is needed? The equilibrium between vapor and liquid. So you will see what is meant by vapor pressure. The pressure exerted by the vapor. So because of this vapor molecules, this liquid surface will experience some pressure because this liquid is covered with these vapor molecules. So these vapor molecules exerts some pressure on this liquid. So this is called vapor pressure. The pressure exerted by the vapor above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure. So vaporization increases with the surface area and temperature. Vaporization increases with the surface area. Vaporization increases with the temperature. But vapor pressure is independent of surface area. Vapor pressure is independent of surface area. Vapor pressure varies exponentially with the temperature. That one I will explain in the next slide. So one more word is required here. Aqueous tension. Aqueous tension. Aqueous water. Tension pressure. So water pressure. So it is a term which is related to pressure and water. So this means the vapor pressure of liquid is called saturated vapor pressure because the atmosphere over the liquid is saturated with vapor of the liquid exerts pressure on the liquid. The vapor pressure of water is known as aqueous tension. Simply what is aqueous tension? the vapor pressure of liquid water is known as aqueous tension. What is boiling point? I told already, as temperature increases, evaporation increases. That means vapor pressure also increases. At a particular temperature, both vapor pressure is equal to atmospheric pressure. That particular temperature is called boiling point. The temperature at which vapor pressure of liquid is equal to atmospheric pressure is called boiling point. So volatile liquids have high vapor pressure. That means low boiling point. So non-volatile liquids like water, so they have low vapor pressure. That means high boiling point. You have to remember one point: boiling point is inversely proportional to volatility. Boiling point is inversely proportional to volatility. This point is important. You note down. Boiling point is inversely proportional to volatility. That means more volatile means less boiling point. More boiling point means less volatile. Next one is factors affecting vapor pressure. First one is nature of the liquid. Factors affecting vapor pressure. Nature of the liquid. Each liquid has a characteristic vapor pressure. Because each liquid has different magnitude of intermolecular forces, the liquids which have weaker intermolecular force tend to escape readily into vapor phase and therefore have greater vapor pressure. For example, dimethyl ether and alcohol have higher vapor pressure than water. So vapor pressure depends on nature of the liquid. Second point, vapor pressure depends on temperature. You see here, heat is providing, temperature raised. As temperature increases, vapor pressure increases. As temperature increases, vapor pressure increases. The effect of temperature on vapor pressure is given by one equation, Clausius-Clapeyron equation. What is that equation? Clausius-Clapeyron equation. This equation gives the relationship between vapor pressure and temperature. You can see here the curve between log P, that means vapor pressure, and 1 by T. It is a straight line with a negative slope. So as temperature increases, vapor pressure increases. There are two cases we can consider in Raoult's law. First one is Raoult's law in case of volatile solute. Raoult's law with a non-volatile solute. Raoult's law with volatile solute, Raoult's law with non-volatile solute. In case of volatile solute, both solvent and solute are found in the vapor state. Here, a vapor pressure will come for both solvent and solute. Example is solution of ethanol. Non-volatile solute, here only solvent has vapor pressure. So both cases are important in point of examination. So we will discuss one by one. So Raoult's law, first one, Raoult's law for volatile solute. So here it is the statement of Raoult's law. The partial vapor pressure of each component, in the solution is directly proportional to the mole fraction of it in the solution. Partial vapor pressure means P is directly proportional to mole fraction, that means X. So that means P is directly proportional to X. So if this solution contains two components 1 and 2, here let the solution contains 1 and 2 components, then P1, let P1 is equal to partial pressure of component 1, P2 is equal to partial pressure of component 2. Let P1 is equal to partial pressure of component 1, P2 is equal to partial pressure of component 2. Then, so you can see here in this diagram, there are two components are there, one with yellow color molecules, another one with blue. So it is in liquid phase. In gaseous phase also, in vapor phase also, you can find both solute and solvent. Here also contains two components, component 1, component 2. In vapor phase, two components are there, means this vapor pressure also will exert because of this two. So here, because of component 1, let partial vapor pressure is P1. Because of component 2, partial pressure is P2. Similarly, X1 and X2 are the mole fractions of components of 1 and 2 in solution respectively. What is first from the beginning again I will explain Raoult's law. What is the statement of Raoult's law? The partial vapor pressure of each component in the solution is directly proportional to the mole fraction of it in the solution. You take one solution contains two components 1 and 2. Let P1 is the partial pressure of component 1. P2 is the partial pressure of component 2. Similarly, X1 and X2 are the mole fractions of component 1 and 2 respectively. Therefore, as per statement, according to Raoult's law, P1 is directly proportional to X1. What is P1? Partial vapor pressure. What is X1? Mole fraction. Partial vapor pressure of component 1 is directly proportional to mole fraction of component 1. P1 is directly proportional to X1, or P1 is equal to, here proportionality is there, proportionality is replaced by is equal to, P1 is equal to P1 naught into X1. What is P1 naught? Here P1 naught is vapor pressure of pure component 1. P1 naught is vapor pressure of pure component 1. So it is about component 1. So you take here in this slide, it is contains only one component, component 1. Here mole fraction of component 1 is X1. So partial pressure is P1. So P1 is equal to P1 naught into X1. But here it is only solute or solvent. Here it contains both solute and solvent. Both are volatile. So here total pressure is related to first component partial pressure and second component partial pressure. So you will see similarly for second component P2 is equal to P2 naught into X2, where P2 naught is vapor pressure of pure component 2. What is P2 naught? P2 naught is equal to vapor pressure of pure component 2. You know Dalton's law of partial pressure. According to Dalton's law of partial pressure, total pressure is equal to sum of partial pressures. So total pressure P is equal to sum of partial pressures, that is P1 plus P2. So that implies you take that P total is equal to P1 plus P2. Substitute the values of P1 and P2. You will get P total is equal to, instead of P1 you write P1 naught into X1. Instead of P2 you write P2 naught into X2. So in this equation you can write X1 plus X2 is equal to 1. Anyway you know X1 plus X2 is equal to 1. That means X1 is equal to 1 minus X2. You write 1 minus X2. So after that you common this X2 term. Therefore finally you got P total is equal to P1 naught plus P2 naught minus P1 naught into X2. So P total is equal to P1 naught plus P2 naught minus P1 naught into X2. It is the Raoult's law for volatile liquids. Raoult's law for volatile liquids. Now you see, it is the Raoult's law for volatile liquids. P total is equal to P1 naught plus P2 naught minus P1 naught into X2. So from this equation you have to explain some conclusions. Following conclusions can be drawn from this equation. First one is total vapor pressure over the solution can be related to the mole fraction of any one component. You check this equation. In this equation, mole fraction, what is P? Here P is there, P total pressure. Here X2 is there. P is related to X2. Total pressure is related to mole fraction of second component only. Suppose in this equation, instead of x1, you write x2 is equal to 1 minus x1. Then you will get in this equation term x1. That means total pressure is related to either x1 or x2. That is first conclusion. Total vapor pressure over the solution can be related to mole fraction of any one component. Total vapor pressure is related to any one component. Second point, you can see it is this equation. This main equation is like a straight line equation. This is in the form of y is equal to mx plus c. Y is equal to mx plus c. What is this y is equal to mx plus c? It is a straight line equation like this. It is a straight line equation. So this is intercept. What is this intercept? C. Here what is the intercept? P1 naught. P1 naught is the intercept. What is y? You compare these two. What is y? Y is P. What is x? What is x? X is x2. What is m slope? M is slope is P2 naught minus P1 naught. P2 naught minus P1 naught. That means as pressure increases, mole fraction increases in the form of straight line, linearly. So total vapor pressure over the solution varies. Total vapor pressure over the solution varies linearly with the mole fraction of component 2. It is a second conclusion. Now you will see third conclusion. Depending on the vapor pressures of the pure components 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. So here again I will explain from the graph. You can see here x1 is equal to this side mole fraction is equal to 0. x1 is equal to 1 to x1 is equal to 0. That means x1 value is decreasing from this side as along x-axis x1 value decreases, at the same time x2 value increases. Now you see x1 decreases means P1 value. It is the curve per partial pressure P1. So as x1 decreases, partial vapor pressure of first component also decreases like this. As x1 decreases, P1 value decreases. Now you see here x2 is equal to 0. Second component mole fraction is equal to 0. This side x2 is equal to 1. So as we move from x origin to this side along x-axis, x2 value increases. So second component mole fraction increases. Per second component mole fraction increases means according to Raoult's law, per second component partial vapor pressure increases. That means you see as x2 increases here linearly partial vapor pressure of second component also increases. As x2 increases, partial pressure increases. As x1 decreases, P1 decreases. So this is what is P1 naught? What is P1 naught? Here x1 is equal to 1. x2 is 0. x2 0 means the total pressure becomes x2 0 means P2 is 0. P2 0. So then in that original equation, in that overall equation, you can write here, next slide it will come. Here x1 is equal to 1, x2 0 means that total pressure is equal to P1 naught. In case of X2 is equal to 1, total solution contains only X2, second component only. That means the total pressure is P2 naught. There is no second, one more solute. Only one type of solute is there, that X2. So that means partial vapor pressure means it is a total pressure. P2 naught means that is equal to total pressure. So this is the total pressure equation. P total is equal to P1 plus P2. In this case, increase. Sometimes it may decrease like this also. So it is about Raoult's law for volatile liquids. It is here special case is there. Both component 1 and 2, both components are volatile. Both components are volatile. Both components are miscible. That means here two components are there, liquid state. Two components are there in vapor phase. Two are in liquid phase, two are in vapor phase. Then here one more formula will come. P1 is equal to Y1 into total pressure. P2 is equal to Y2 into total pressure. Already you know, as per Raoult's law, first formula, P1 is equal to X1 into P1 naught. What is X1? Mole fraction of component 1 in this phase, in liquid phase. X1 means mole fraction in liquid phase. Here I will explain. Here X1 and X2. X1 per component 1, X2 per component 2, on which state here? Liquid state. If it is in vapor phase, mole fraction is Y1. Per component 1, mole fraction in vapor phase is Y1. Per component 2, mole fraction in vapor phase is Y2. Here Y1 is mole fraction of component 1. X1 is also mole fraction of component 1. But difference is there in liquid phase and in vapor phase. So if both are in volatile, both are miscible, then Raoult's law will come like this. P1 is equal to, you can use this is also, P1 is equal to Y1 into P total. What is Y1? Partial, what is Y1? Mole fraction of component 1 in vapor phase. So here completely given. Composition in vapor phase. The composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the components. If Y1 and Y2, are the mole fractions of two components, if Y1 and Y2 are the mole fractions of two components and 1 and 2 in the vapor phase, that is important here. Y1 and Y2 are the mole fractions, Y1 and Y2 are the mole fractions in the vapor phase. Then P1 is equal to Y1 into P. P2 is equal to Y2 into P. So that means in general Pi per component I, partial pressure Pi is equal to Yi into total pressure. So based on this formula, one example solved question is there in our textbook. Okay, it is about Raoult's law of volatile liquids. Now second case, that is Raoult's law for non-volatile solute. So before going to discuss second case, we will see here non-volatile solute. When a non-volatile solute is added to a solvent, when a non-volatile solute is added to a solvent, the vapor pressure decreases. Why? You see here it is pure solvent. In here pure solvent. This is a pure solvent. Total surface contains only solvent molecules. This surface contains only solvent molecules. Here, because of these collisions between these molecules, some solvent molecules will go to vapor phase. So they will exert pressure, that is called vapor pressure. of pure solvent. In this case, solvent and solute are there. You see, when non-volatile solute is added, that is this black pot, black molecules. This non-volatile solute is added, that's why some solute molecules came and occupy the surface position also, because solution is a homogeneous mixture. That's why this solute can occupy anywhere, because here solute is present, here also it can present. So now surface area, you compare here, number of solvent molecules are less, here number of solvent molecules are more, because here total surface is occupied by only solvent. But in this case, surface is occupied by both solute and solvent. So surface area of solvent molecules decreases, so vapor pressure decreases. This is called lowering of vapor pressure. When a non-volatile solute is added to a solvent, the vapor pressure decreases, because in a solution the surface is not only occupied by solvent molecules but also by solute molecules. So this one you see, solvent alone means here pressure is more. Here solvent and solute, this solution contains solvent and solute, so that's why number of molecules came into vapor phase. So number of vapor molecules decreases, so hence vapor pressure decreases. By adding non-volatile solute, its vapor pressure decreases. This is called lowering of vapor pressure. The number of molecules of solvent present on surface are relatively less in solution than that of pure solvent, as some solvent molecules on the surface are displaced by solute molecules. The number of molecules converting to vapor is the vapor pressure of pure solvent. P is the vapor pressure of the solution. P0 is the vapor pressure of pure solvent and P is the vapor pressure of the solution. Then the difference between P0 and P0 minus P is called lowering of vapor pressure. For example, I will give one value. Vapor pressure of pure solvent, you say 100. After adding non-volatile solute, its vapor pressure becomes 80. So it is 100, this one 80. How much decreased? 20. So that 20 is called lowering of vapor pressure. The decrease in vapor pressure from P0 minus P is called lowering of vapor pressure. 20 is decreased out of 100. P0 minus P is decreased out of P0. So out of P0 you are comparing, you are comparatively expressing. So that means relative expression. So it is relative lowering of vapor pressure. What is relative lowering of vapor pressure? P0 minus P by P0. It is relative lowering of vapor pressure. Next we will move to Raoult's law. Raoult's law for solution containing non-volatile solute. It is very, very important. Raoult's law for solution containing non-volatile solute. This is statement. At a given temperature, the relative lowering vapor pressure of solution is equal to the mole fraction of the solute, mole fraction of the non-volatile solute. At a given temperature, the relative lowering vapor pressure of a solution is equal to the mole fraction of the solute. So derivation, I will start. We know that from Raoult's law, P solution is equal to P1 plus P2. What is P1? Vapor pressure of partial vapor pressure of component 1. It is partial vapor pressure of component 2. Therefore, vapor pressure of solution is equal to P1 naught x1 plus P2 naught x2. Because P1 naught value no, that one written, P2 naught value substituted. Therefore, P solution is equal to P1 naught into X1. But here 0 written. Why here 0 written? Because it is a non-volatile solute. So there is no vapor pressure from solute side. Because it is non-volatile solute. Its vapor pressure is 0. So P2 naught is 0. Therefore P solution is equal to P1 naught into X1. Why? Since P2 naught is 0, because B is a non-volatile solute. So next, therefore P solution is equal to X1 into P1 naught. But you know the value X1 plus X2 is equal to 1. Instead of X1, you can write 1 minus X2. Therefore, P solution is equal to 1 minus X2 into P1 naught. That means you shift this P1, P solution minus P1 naught is equal to minus X2 into P1 naught. You multiply entire equation with minus and shift this P1 naught to this side. Then P1 naught minus P solution by P1 naught is equal to X2. You know P1 naught minus P. What is P1 naught minus P? Already I explained. P1 naught minus P is lowering of vapor pressure. P1 naught minus P by P1 naught. P1 minus P by P1 naught is relative lowering of vapor pressure. That means relative lowering of vapor pressure is equal to mole fraction of solute. X2 is mole fraction of solute. So simply you can remember what is Raoult's law. At constant temperature, relative lowering vapor pressure of a solution is equal to mole fraction of solute. RLVP is equal to X2 at constant temperature. This is about Raoult's law. In exam they will ask state and explain Raoult's law of volatile liquids. That means you have to write that graph 3 conclusions. First one, Raoult's law, state and explain Raoult's law of non-volatile solute. So this is the statement. At constant temperature, relative lowering vapor pressure of solution is equal to mole fraction of solute. So there are some limitations for Raoult's law. What are that limitations? It is applicable for very dilute solutions only. It is applicable for dilute solutions containing non-volatile solute only. It is applicable for solutions containing solutes which neither associate nor dissociate. That means that type of solutions are called ideal solutions. This ideal solution is next topic. Our next class I will explain about ideal solutions. These are about limitations of Raoult's law. So in today's class what I explained about vapor pressure, Raoult's law of 2 cases. Okay, thank you.